Welcome to G Fun Facts Online. Beneath our feet, the Earth's crust is a mosaic of ancient battlegrounds. For billions of years, continents have collided and ripped apart, leaving behind a legacy of deep, hidden wounds. For eons, these scars can lie dormant, buried under kilometers of rock. But when conditions are right, these ancient weaknesses can become the focus of one of the most terrifying forces on our planet: supervolcanoes. A supervolcano isn't your typical cone-shaped mountain. It's a volcano that has produced an eruption of magnitude 8 on the Volcano Explosivity Index, the highest level possible. This means it has ejected more than 1,000 cubic kilometers of material, enough to bury an entire continent in ash and plunge the world into a volcanic winter. Instead of building a mountain, a super-eruption causes the ground to collapse into a vast depression called a caldera, which can be dozens of kilometers wide. For decades, the leading theory for these immense volcanic centers was the mantle plume, or hotspot model. This theory imagined a column of super-hot rock rising from deep within the Earth, punching through a tectonic plate to create a volcano. But a growing body of evidence suggests this isn't the whole story. The true genesis of these behemoths lies in a complex interplay between the heat of the mantle and the ancient architecture of the continents themselves. These ancient scars act as focusing lenses for geological forces, creating the perfect conditions for magma to be generated, stored, and brewed into an apocalyptic force. To understand how these scars create supervolcanoes, we must first understand their nature. Continents are not uniform slabs of rock. At their hearts lie ancient, stable cores, known as cratons. These are immensely old blocks of the Earth's rigid outer layer that have survived the cycles of continental merging and splitting for over 500 million years, with some being over 2 billion years old. They are thick, strong, and have deep roots extending hundreds of kilometers into the mantle. But cratons are bordered by younger, more mobile belts of rock. The boundaries where these different geological terrains have been welded together are known as suture zones. These are the geological equivalent of scar tissue, marking the place where ancient oceans closed and continents collided. While the collision is long over, the suture zone remains a fundamental discontinuity, a zone of structural weakness that cuts deep into the lithosphere. Furthermore, continents are scarred by rifts, linear zones where the lithosphere has been stretched and pulled apart. Sometimes this leads to the formation of a new ocean basin, but often, the process fails, leaving behind a failed rift, a thinned and heavily faulted stretch of crust that remains a permanent zone of weakness. These ancient features, the strong edges of cratons, the deep weaknesses of suture zones, and the thinned crust of ancient rifts, are the scars that set the stage for supervolcanism. They create profound variations in the thickness and strength of the Earth's lithosphere, and this heterogeneity is the key. The generation of the colossal amounts of magma required for a super-eruption is the first critical step, and new evidence from two of Earth's most famous supervolcanoes, Yellowstone and Toba, reveals a story that is deeply dependent on these scars. The Yellowstone caldera in Wyoming is perhaps the world's most well-known supervolcano. For years, it was considered the textbook example of a hotspot, with the North American plate drifting over a stationary mantle plume. However, recent, sophisticated seismic imaging has failed to find conclusive evidence of a deep, continuous plume extending from the core mantle boundary. This has led to a revolutionary new interpretation that places an ancient tectonic scar at the heart of the Yellowstone story. This scar is the ghostly remnant of the Farallon Plate, an ancient oceanic plate that began sliding or subducting beneath North America around 200 million years ago. About 30 million years ago, this subducting plate began to fragment and sink deep into the mantle. Instead of a simple plume, new models suggest that the Yellowstone system is powered by the complex interactions of this foundering, broken slab. As sections of the cold, dense Farallon slab tear and sink, they displace the hotter, more buoyant mantle material around them. This creates upwellings of hot mantle that aren't a narrow plume, but a broader zone of rising heat. Crucially, this process occurs beneath a continental plate that has its own complex history. The rising hot material is channeled and focused by pre-existing structures in the overlying North American plate. This interaction between the death throes of an ancient oceanic plate and the inherited architecture of the continent above is what fuels Yellowstone. The famous hotspot track is not the result of the plate moving over a fixed plume, but rather the propagation of volcanic activity along a pre-existing zone of weakness that is being progressively heated from below. On the other side of the world, in Sumatra, Indonesia, lies the Toba caldera, the site of the largest known explosive eruption in the last 25 million years. Around 74,000 years ago, the Toba super-eruption ejected an estimated 800 cubic kilometers of material. Like Yellowstone, Toba's existence cannot be explained by a simple subduction zone model. The key to its immense power appears to be a very specific type of ancient scar on the subducting plate itself. The Indo-Australian plate that is diving beneath Sumatra is bisected by a massive 500-kilometer-long scar known as the Investigator Fracture Zone, or IFZ. As this specific, weakened, and water-rich section of the oceanic plate is subducted, it behaves differently from the surrounding crust. Seismic models reveal that the subduction of the IFZ directly beneath Toba leads to an anomalous release of volatiles, primarily water, at a depth of around 150 kilometers. This water, carried down into the mantle, acts as a powerful flux, dramatically lowering the melting temperature of the overlying mantle wedge. This triggers massive scale melting, far greater than what occurs along a typical subduction zone. The result is an anomalously high production of magma, directly linked to the subduction of this ancient oceanic scar. These stories highlight a broader principle. Lithospheric weaknesses are critical for generating large volumes of magma. Another mechanism, often linked to these ancient scars, is edge-driven convection. This occurs at the boundary between thick, cold cratonic lithosphere and thinner, warmer lithosphere. The sharp temperature difference can induce a small-scale convection cell, causing a passive upwelling of hot mantle material right next to the craton's edge. This essentially creates a predisposed hot lane for magma generation. A more dramatic process is lithospheric delamination. Over time, the lowest part of the thick, cold lithosphere beneath a continent can become unstable, detach, and sink into the hot mantle below. Hot, buoyant mantle material then rushes in to fill the void, coming into direct contact with the base of the crust. This sudden, intense heating can trigger widespread melting and a powerful burst of volcanism. This represents a catastrophic failure of an ancient lithospheric structure, leading directly to the conditions needed for massive magma production. But generating a colossal amount of magma deep in the mantle is only the first part of the story. This magma must then ascend through tens of kilometers of crust and accumulate in a shallow reservoir without erupting prematurely. Once again, ancient scars play a crucial role, providing the plumbing system for this colossal undertaking. Geophysical studies at supervolcanoes like Yellowstone have revealed a complex, multi-level magmatic system. There isn't a single massive balloon of molten rock, but at least two large reservoirs. The first storage zone is located deep in the crust, near the boundary with the mantle. Here, the initial, hot, basaltic magma pools and stalls. At Yellowstone, this lower reservoir is immense, estimated to contain some 46,000 cubic kilometers of hot, partially molten rock, enough to fill the Grand Canyon more than 11 times. It's a vast region of magmatic mush, mostly solid, but with pockets of liquid melt. Above this deep reservoir sits a smaller, shallower magma chamber, located within the upper 5 to 15 kilometers of the crust. At Yellowstone, this chamber is still enormous, with a volume of around 10,000 cubic kilometers. This is the chamber that directly feeds the super-eruptions. It is here that the magma evolves into its most explosive form. So how does magma move between these levels and accumulate in such vast quantities? The answer lies in the exploitation of pre-existing weaknesses. Ancient suture zones, fault systems, and rift valleys are deep-seated structural flaws that act as preferential pathways for rising magma. In extensional settings, where the crust is being pulled apart, it is thinned and fractured. Magma can easily intrude along these reactivated ancient faults, following the path of least resistance. These weak zones don't just provide a pathway, they also help in the accumulation of magma. For a giant magma chamber to form, the crust must be able to accommodate this vast volume of molten rock. In these tectonically active weakened zones, the warm crust is more pliable. It can stretch and inflate as the magma chamber grows, preventing the buildup of pressure that would trigger smaller, more frequent eruptions. This allows magma to be stored for hundreds of thousands of years. In essence, the ancient scar creates a soft spot in the crust, a perfect location to inflate a truly monstrous magma body. The magma that initially forms in the mantle is typically basaltic, hot, fluid, and not especially explosive. The cataclysmic power of a super-eruption comes from a different kind of magma, rhyolite. Rhyolitic magma is thick, sticky, rich in silica, and saturated with dissolved gases. The journey from benign basalt to explosive rhyolite happens within the crustal magma chambers, and ancient weak zones play a starring role. The process is known as magma evolution, and it involves two key mechanisms: crustal assimilation and fractional crystallization. As the initial basaltic magma pools in the shallower crustal chamber, its intense heat begins to melt the surrounding crustal rocks. This is crustal assimilation. The magma literally digests the walls of its chamber. This is where the ancient scar becomes paramount. Continental crust is typically rich in silica. By melting and incorporating large amounts of this silica-rich crust, the magma's chemical composition is fundamentally altered. It becomes progressively more silicic, evolving towards explosive rhyolite. The faults and fractures within these weak zones increase the surface area for this interaction, making the assimilation process more efficient. Simultaneously, as the magma body cools, minerals begin to crystallize. The first minerals to crystallize are rich in magnesium and iron. Being denser, they settle out and accumulate at the bottom of the chamber. This process removes certain elements from the melt, further enriching the remaining liquid in silica and volatiles. Over hundreds of thousands of years, these processes work in concert. The magma body slowly differentiates, becoming a stratified system with a less evolved basaltic component at the base and an increasingly large, highly evolved, and volatile-rich rhyolitic cap at the top. This upper layer of viscous, gas-charged rhyolite is the fuel for a super-eruption. It is a ticking time bomb, slowly accumulating and pressurizing, waiting for a trigger. After millennia of slow accumulation, a massive body of explosive magma sits just a few kilometers beneath the surface. What finally pushes it over the edge? One potential trigger is the rapid injection of a new batch of hot, basaltic magma from below. This recharge event can cause a rapid increase in temperature and pressure, causing volatiles to exsolve rapidly, like shaking a soda bottle before opening it. Another trigger could be tectonic. A large earthquake on one of the reactivated faults that define the weak zone could fracture the roof of the magma chamber. This sudden depressurization would allow the dissolved gases within the rhyolite to expand violently, initiating a runaway explosive eruption. Finally, the sheer buoyancy of the massive low-density rhyolitic magma itself might be enough. As the chamber grows, the upward pressure on its roof increases. Eventually, the roof rock, already weakened and fractured, may simply fail under the strain. Once the eruption begins, the rapid withdrawal of thousands of cubic kilometers of magma removes support for the overlying crust. The roof founders, collapsing into the now empty chamber and creating the vast caldera that is the defining surface expression of a supervolcano. From the deep mantle to the shallow crust, the story of a supervolcano is inextricably linked to the deep history of our planet. They are not random acts of geological violence. They are the dramatic culmination of a chain of events that begins with the ancient scars that wrinkle the face of our world. The collision of a continent a billion years ago, or the tearing of a plate hundreds of millions of years past, can create a zone of weakness that, through a confluence of geological processes, becomes the birthplace of a planetary-scale catastrophe. These ancient wounds remind us that the Earth's past is never truly buried, and that its oldest scars can give rise to its most powerful fury.